this video, we're going to talk about Venn diagrams. So a Venn diagram is a way of representing a set or a group of sets in a visual way. So it's a good tool to have, particularly if you're a visual person. In terms of reporting data, think of data being organized into sets. A Venn diagram is a great way to report data if you're interested in things that different sets have in common and then things they don't have in common. So we're going to look at how you draw a Venn diagram, particularly when your data looks specific in terms of how one set relates to another. You're probably familiar with a Venn diagram. You've probably seen one before, and you've probably seen it formatted a very specific way. As it turns out, there's a bunch of different ways to format a Venn diagram depending on the type of relationship we're trying to show. And then we'll also talk about set operations. So think of that as like algebra. Think of it like set algebra. Different things you can do to sets, to combine them together, to compare them, those kinds of things. Okay, so in many situations, we want to explore the relationship. In other words, the commonalities between sets. Also, we want to think of how they relate to the general context of a problem. Think of them as being somehow within the context of something else. So when we look at our individual sets, think of them as further groupings within the bigger picture. What we're going to do here is we're going to represent the individual sets and the bigger picture using what we call a Venn diagram. So we're going to start big picture and we're going to work our way in. We need to define what we call the universal set. So the universal set is going to be a general big picture set that contains all elements under discussion. So we're thinking of grouping elements, all the elements that we're then taking and grouping further into our specific individual sets. All of those elements together make up what we call the universal set. So you can think of the universal set as sort of the context for your problem, for your situation. So visually, we're going to represent the universal set as a rectangle, and we're going to label it with a capital U. So that means this U is kind of off limits as a label for other situations. So if you wanted to use a U to label your set, you can't use it. You're going to have to come up with a different variable, different label, because U specifically stands for the universal set. So visually, our subsets, the actual sets we're interested in inside of the universal set, the further groupings, we've taken all these big elements and we put them into smaller groups based on commonalities, based on things that these elements have in common. These subsets are going to be represented as circles, and this is probably what you're used to seeing if you've seen a Venn diagram before. So we can consider a single set or two sets, more sets. We can go 3, we can go 4. We can look at any number of sets. We're going to start with just a single set and then 2 sets in this section. Now our sets may or may not have things in common. So if we're looking at a single set, we're just looking at a single grouping. If we're looking at 2 sets, there are different situations depending on how the sets relate to one another. So more than likely, when you've seen a Venn diagram, you've specifically seen it with 2 sets, and you've specifically seen it drawn in a certain way. A Venn diagram can be used more generally than what you've actually seen. We can actually draw a Venn diagram with a single set. That means we'll draw a single circle within the rectangle representing our universal set. So this is an example of a really, really basic Venn diagram. Believe it or not, that's a Venn diagram. So the rectangle, anything inside that rectangle is within our universal set U. Think of all the contents within the rectangle as being all the elements under consideration. They're all the things that we could further group based on commonalities or leave outside of the set based on the fact that they don't share the particular things we're interested in. Now within the universal set, depending on what sort of things we're looking for, what our set represents, we draw a circle, and anything within that circle is considered to be an element that was further grouped. We can think of this circle, what we're calling A, as being a subset of the universal set. So its contents are contents within the universal set. They're just items that happen to have been grouped further because somehow they meet our criteria for being within this set. Now, one thing I want you to keep in mind, though, is that this circle is inside of the universal set. So when we talk about the universal set, we're talking about everything inside the rectangle. This includes things that are outside of the circle as well as things that are inside. Everything that's anywhere in the rectangle is considered to be part of the universal set. Whether it's been further grouped or not, it is part of this universal set. So let's look at an actual one with some contents in order to determine what some of these sets are going to look like. So here's our Venn diagram. We have our universal set and we have what we're calling the set A. And our individual elements are 1, 5, 6, 7, and 9. So first off, let's define the universal set. What are the contents within the universal set? Well, that's defined as any element that exists somewhere within the rectangle, anywhere within the rectangle. Well, 7 and 9 are easy to spot because they're definitely within the rectangle. But remember, 1, 5, and 6, although they've been further grouped into this set we're calling A, they're also still inside of the rectangle, so they are also a part of the universal set. So the universal set is going to have all 5 of these elements, the 3 that have been grouped further, and then the 2 that weren't. So the universal set is going to be 1, 5, 6, 7, and 9. Now what about the set A? That's going to consist of all the elements in the universal set that were then grouped further. We can find those inside the circle representing that set. So that's going to be the elements 1, 5, and 6. And then the other set we could define would be the set of elements that are in U that are not in A. In other words, they're in the universal set, but they didn't make it into the set A for some reason. That's going to be the elements 7 and 9. So anytime we look at our circles, we may have 1, we may have 2, we may have 3. Things may be grouped into the circles. There will almost always be things that are not grouped into them, things still in the universal set that didn't somehow make it into our subsets that we're looking at. We can't forget those elements. Those were under consideration, but for some reason they weren't grouped any further. They are still considered part of the problem though. They are still components, they are still elements that are part of the universal set. So in this case, the elements in U that are not in A are going to be 7 and 9. So really basic situation, this is what we're looking at. Now a Venn diagram like this is not especially meaningful. Venn diagrams are used to demonstrate relationships. Well, this shows us the relationship of A within the universal set, but it's not especially interesting. It just shows us that we grouped some elements a little further and we didn't group other ones. What we're really interested in is Venn diagrams where we can draw 2 sets, where we can compare sets together, what they have in common and what they don't have in common. Now, how we draw the diagram is going to depend on if they have anything in common, and if so, what do they have in common? So to look at all the different possibilities, we're going to think in terms of an example, and we're going to look at all the different ways we could get data from this example and the kind of diagram we would draw in order to represent that particular situation. So here's the setup. We want to organize a blood drive on campus. So we're going to take a survey to determine students' willingness to donate blood and their willingness to help with a breakfast for blood donors. And then after the survey, we create 2 sets. So the set A is defined as everyone who's willing to donate blood, and the set B is defined as everyone who's willing to help with breakfast. Now, first thing we have to consider, always start here. We want to think about what is the universal set? What is the context for the problem? If we're thinking about all the elements under question, all the ones that may be put into A, all the ones that may be put into B, everyone in question, that represents the universal set. Think of it as the context for the problem. Well, here we're talking about doing a survey on campus. So our universal set is going to be all the students who were surveyed. Some people may fall into the set A, some people may fall into the set B, some people may fall into both sets, some people may fall into neither. But the universal set, in terms of who we're grouping a little bit further, that's going to be all the individuals that were surveyed. So that's going to represent you in this case. Now let's focus on A and B. How are A and B related in terms of these survey results? So one possibility is that no students who were willing to donate blood are willing to serve breakfast, and vice versa. In other words, if they said they donate blood, they said they would not help with breakfast. If they said they would help with breakfast, they said they wouldn't donate blood. So we had volunteers, but we didn't have any volunteers who were willing to do both things. So that means anyone grouped into the set A is not grouped into the set B, and vice versa. In this case, A and B are said to be disjoint. That's the term for this. Disjoint means they have no elements in common. So we took the elements in the universal set. We took the names of all these students. We grouped them a little bit further, but we didn't have anyone that fell under both categories, that fell into both sets. Now, if this is the case, if there's no elements in common, then you're going to draw circles that don't overlap. What you're used to saying more than likely is two circles that overlap. Well, you overlap them in order to show what they have in common. If these two sets don't actually have any elements in common, then by drawing the overlap, you're just going to have an empty overlap. So it's perfectly fine just to draw the two sets and leave them just separate, leave them disjoint, leave them separate. So anyone who falls into A is willing to donate blood. Anyone who falls into B is willing to serve breakfast. What about someone who's left inside the rectangle but didn't go into A and didn't go into B? Well, what we would say is that they were surveyed, they're part of the universal set, but they said they didn't want to donate blood. They said they weren't willing to help with breakfast. So we do have to consider those. They weren't further grouped, but they are part of the universal set. So that's going to be one possibility, fairly unlikely possibility, but it is still something we have to consider. Now here's another possibility. All students who were willing to donate blood are also willing to help with breakfast, but not necessarily the reverse. So anyone who said they'd donate blood also said they'd help with breakfast. And then there are also some other people who said, yes, I'll help with breakfast, but for some reason they chose not to donate blood. So if this is the case, we would say that A, our donators, A is a proper subset of B. Everyone in A is also contained in B. Everyone who donated blood also helps with breakfast, but there are potentially some other individuals who would help with breakfast that don't fall into the set of donators. So our notation here, we looked at this notation in the last video, A is a proper subset of B. A is contained in B. Every element in A can also be found in B. Now if this is the case, A is within B, and they're both within the context of the universal set. Because A is a proper subset of B, we can actually draw it inside of the circle for B. So everyone who falls into A also falls into B. So if we draw them in the circle A, they fall under A and they fall under B. Now there's a region inside of B that doesn't overlap with A. Say someone was willing to help with breakfast, but they didn't want to donate blood. Well, they would fall into that additional ring that doesn't fall under A but does fall under B. And again, anyone who's outside of the circles, that means the same thing. It means they were surveyed, but they weren't willing to help with either activity. So that again, fairly uncommon, but also a possibility for what could happen. Now here's a third possibility. The same students who are willing to donate blood are also willing to serve breakfast. In other words, anyone who volunteered for one activity automatically volunteered for the other one. No exceptions. Everyone volunteered for both, or they didn't volunteer at all. If this is the case, then our donators, our set of donators and our set of breakfast helpers is actually going to be the same. We would say that these two sets are equal. Remember, the term equal means the sets have the exact same contents. Well, if everyone who falls under the donating category also falls under the serving breakfast category, then we would say that those two sets are the same. They are equal. If that's the case, then we're close to this situation, but now A is not a proper subset of B. A is equal to B. So imagine enlarging the circle for A. The bigger the circle for A, the more in A that are also in B. If we were to enlarge it fully so that they overlap, then that means everyone in A is also contained in B and vice versa. So if they are equal, All we really need is one circle. It's actually two circles in one though. So it's not the same thing as the diagram on the first page where we only have that one circle within the universal set, within that rectangle. Here it's really two circles, but they coincide. The set for A represented as one circle, the set for B represented as another circle. Well, they happen to have all of the same contents, so we draw them in such a way that they overlap. In order to indicate that we are looking at two sets though, we need to notate that. So if we just drew the circle, there's no way to know, well, did we just group things into one set or not? It probably would look like we just grouped things into one set. In order to indicate that there really were two sets, but it just so happened that they both had all of the same contents, we can label it with this kind of notation and show that A is equal to B, and so this circle represents both A and B. So these three possibilities are all fairly unlikely. The most likely possibility is going to correspond to the Venn diagram that you're probably used to seeing. So our last possibility is that some of the students who are willing to donate blood are also willing to serve breakfast. Some, but not all of them. So what that means is that there are 4 situations that could occur. We have some students who will donate blood and who will also serve breakfast. So there is a category of students who are willing to do that. There will also be some people who said they'd donate blood but said they wouldn't serve breakfast. There will also be people who said they'd serve breakfast but wouldn't donate blood. And then again, there's still that pool of people who were surveyed but decided they weren't willing to do either. So in order to indicate that these two sets have some things in common, but not necessarily all things in common, we draw our two circles and we draw them with an overlapping region in the middle. So based on where we fall in this diagram, we can determine what did this person say when they responded to this survey. So the overlapping region is where the circles coincide. It's where they overlap. Notice it's shaded darker. The shading is going to help you identify what am I really looking at. So that shaded region shows where those two circles overlap. So we have 4 different regions. We have the overlapping shaded region, and then regions 2 and 3 inside the circles but not within the overlap. And then region 4 is within the rectangle but not grouped into the circles. So what can we say about someone in region 1? Well, if they're in region 1, they fall into the circle for A, and they also fall into the circle for B. Well, if they fall into the circle of A, they were willing to donate blood, and if they fall into the circle for B, they were willing to serve breakfast. If they're in the overlap, they're within both circles at the same time. So that means they were willing to serve blood. They were willing to donate blood and serve breakfast, both at the same time. They fell under both categories. Now, what if someone falls into region 2? That means they're in the circle for A, but they're not within the portion overlapping with B. That means they're willing to serve blood. They fall into the category for A, but they're not willing to do breakfast. Because they're outside of that region that contains the circle for B, they're only willing to do the one activity. Now, same kind of thing for 3. 3 is within the circle for B, so we know these people are willing to serve breakfast. They fall under that category, but they don't fall within the overlapping region, which means they're not willing to donate blood. They'll only do one or the other. And then region 4, we can't forget those people. Remember, they're in the universal set, but they haven't been further grouped into the circles representing our survey results. So that means they were surveyed, but they didn't actually volunteer for either activity. So let's categorize things a little bit further, just based on what we see, based on an actual Venn diagram with some actual contents. So based on how a set is described, where we find it in the Venn diagram is going to differ. We have to be very specific about what we mean when we describe a particular set. What is it in? What is it outside of? Those kinds of things we have to be really, really careful about. So we're going to use this Venn diagram in order to define all of these different sets. So it's just a visual way of representing these sets. We want to actually write them out in roster method, actually make a list of what the sets are that are represented in this diagram. So the first set we want is U, the universal set. Now remember, when we say we want the universal set, that means anything anywhere within the rectangle. That's not just things that are in the rectangle by itself, but also elements that have been further grouped into the circles. So any element that you can find anywhere within this diagram falls into the universal set. Now I want you to be careful here in terms of labeling. Our sets are A, B, and then U. The Roman numerals, this is 1, this is 2, this is 3, and this is 4. Those are labels for regions. So I had them labeled as just 1, 2, 3, 4 on the previous page. Here they're being labeled as Roman numerals. So those are not considered elements in the set. They are just labels. The actual elements are the letters from A to G. Those are the actual elements that are then being considered as part of a set. So when we're looking at the universal set, we're looking at anything that is anywhere within the rectangle. So we have A, B, and C, which are exclusive to A. We have D, which is in A and B at the same time. We have E, which is exclusive to B. And then we also have F and G, which are outside of the circles entirely. So the universal set is going to be all the elements from A to G. And if we identify the regions associated with the universal set, that's going to be all 4 regions. All 4 of these regions represent the rectangle as a whole, so all 4 of these regions make up the universal set. Now what about the set A? Notice it doesn't say A only or A exclusively. It's just A in general. In other words, anything that's anywhere within the circle for A makes up the set A. This includes things that are only in A, as well as things that overlap with whatever other sets we have in this particular diagram. So the set A, again, our circle for A, it's going to be AA, B, C, and then D. That's going to be the circle A. So in terms of the regions, we have region 1, we have region 2. Those are going to be the 2 regions that make up the circle for A and then make up the set A. Now what about the set B? That's going to be anything that's anywhere within the circle for B. So anything that's in B exclusively, and then anything that's in B's overlap. So that's going to be the elements D and E, which are regions 2 and regions 3. Now notice as I'm making these lists, I'm listing things in a particular order. I'm listing alphabetically. I'm listing alphabetically because it's a meaningful way to order. But say for instance I wanted just B and then the overlap. That would be E then D instead of D then E. That is perfectly fine. It's not a big deal to do it that way. The benefit of listing things in a meaningful order though is particularly when the lists get long, it's going to be easier to identify if you've left something off. So if everything is in sort of a meaningful order, it's going to be easy to spot things that are missing or maybe things that have been added in that shouldn't have been there. If things are in sort of a random order, it's going to be harder to spot what you might have left out of the set. So writing things in some kind of order is not necessarily a bad thing to do. It's not essential, but it's something that's a good habit, something to think about doing. Okay, so now let's be a little bit more specific. The set of elements in A, but not in B. So they are in A, but they're not in B. So they're in A, but they are not in B. That's going to be anything that's in the circle for A, not including what's in the overlap. So that's going to be the elements A, B, and C. And notice that's only represented by one region. It's the one portion of the circle where we actually have something within A that's not within any other set. So that's going to be the region 1. The set of elements in B, but not in A. Now again, that's going to be anything that's in B that's not also in A. So that's going to be the set with the element E, and that's going to be just the region 3. How about the set of elements in U that are not in A? Okay, now here's where we're going to have to be careful. This is a very visual kind of thing. They're in the universal set, but they're not in the set A. The way to visualize this is imagine just imagine pulling out the set A. The easiest way to do that without getting a pair of scissors and actually cutting it out is just take it and cover it up. So we want everything in U except the things that were in A. So imagine just deleting that set A and then keeping everything else that's within the diagram. Well, that's going to leave us with things that are exclusive to B, and then also elements that weren't further grouped into A or B. So that's going to be E, F, and G, and that's going to be the regions 3 and 4. Those are going to be the two regions representing things that are in the universal set but not in the set A, deleting that set A. Now what about the elements in U that are not in B? Same kind of thing. We want the universal set, the whole rectangle, except things that have been further grouped into B. So imagine deleting B. Anything that's left over in the diagram anywhere else would be included. It's in U, but it's not in B. So A, B, and C, which are exclusive to A, and then F and G, which are exclusive to the universal set, not further grouped. So A, B, C, F, and G, and that's going to be the region 1 and then the region 4. Okay, the set of elements in both A and B. So it has to be in the circle for A, and it has to be in the circle for B. We can identify that as the overlapping region. So in this case, there's only going to be one element. Remember that Roman numeral, that's a label. So the only element in that set is going to be the element D, which is represented by region 2. And then also the set of elements in U, but not in A or B. So it's not in A and it's not in B at the same time. Well, what does that leave us with? That just leaves us with these two elements that are within the universal set, but not in A or in B. So that's going to be the elements F and G. And notice that's only going to be one region as well. That's just going to be the region 4. So it's going to be everything that's in the rectangle if you were to remove those circles from the diagram. Okay. So based on this, now I want you to notice how much of a pain it was to write all of that. The set of elements in A but not in B. Would you really want to have to write that every single time in order to describe a particular part of the diagram? The answer is probably no. It's kind of tedious to write that out. It's very descriptive. We know when we write something like that out what sort of things we're looking for and what sort of things we're not looking for. But writing something like that out over and over and over again would be very tedious. So fortunately, we have some notations that are going to allow us to represent these different locations within the diagram in a more concise way, in a symbolic way. And it's also going to define what we think of as our set operations. You can think of them kind of like algebra that's being done to sets. It's not truly algebra, but it's going to look similar to some of the things that we do algebraically. So in most cases, we can identify an operation with what it kind of looks like algebraically in terms of your addition, subtraction, multiplication, division. So we have 3 operations. We call them the complement operation, the intersection operation, and the union operation. So we're going to start with the complement, and that's complement with an E, not complement with an I. Complement spelled like this, it means, how do you put what that means? It means sort of it adds to it and makes it whole. That's what complement means. So if you think of like complementary angles add up to a full 90 degrees. So one completes the other. You can think of it that way. Complement with an I means you're complementing someone. So not the same thing. So the complement of the set A, our notation is going to be A with an apostrophe. We don't actually call this an apostrophe, we call it a prime. So this is the prime symbol. So A prime, or we can say A complement. You can read that either way. A prime, A complement. That's defined as all the elements that are in U, they're in the universal set, but not in A. So they're in U, they're somewhere in the diagram, somewhere in the rectangle, but they're not in the set A. So the way we would write this in set builder notation, if we were to really describe this symbolically, this is going to be all X such that X is an element of U, it is contained in U, and X is not an element in A. So anything that's anywhere in the diagram but not within the circle for A makes up the complement for A. So in a Venn diagram, that's going to be everything outside of the circle A. Now I said you can kind of think of these algebraically. The complement you can kind of think like subtraction. It's like you're subtracting out the set. So if you're taking a complement, you can think of that as kind of taking the set A and subtracting it out of the diagram or out of the set. You determine what's left over within the universal set once you remove A from the picture. So we'll look at this in terms of a Venn diagram, and then we'll also look at this in terms of just actual sets written out. So we want a complement based on this diagram. So we have the universal set, we have the elements from, it looks like 1 to 9, so natural numbers from 1 to 9. And we want to determine a complement. Well, here's A. So a complement says take the set A and throw it away, delete it, pull it out of the diagram. Anything that's left over as an element, once we remove the set A, is considered to be part of a complement. So that's going to be the elements 2, 5, 6, 8, and 9. Those are the remaining elements we have in the diagram once A is removed. Now we can do the same kind of thing without the Venn diagram. As long as you know what the universal set is and you know what your individual subsets look like within that context, you can find a complement without an actual diagram. So for example, if U is equal to the letters from A to G, and then we've defined the subsets A and B as B, C, D, and then A, C, F respectively, we want to determine A complement and B complement. So again, think of this like subtracting. If you're taking a complement, you're taking all the elements that are in A and you're subtracting them out of the universal set. You're pulling them out and you're determining what's left over once you remove those specific elements. So if A is going to be B, C, and D, and notice first off, notice that this is a subset of the universal set. The universal set is always the largest set within the context of the problem. It forms all the elements that we're then grouping further. They may be grouped into one set, they may be grouped into another, they may be grouped in both, they may not be grouped at all. But we think of it as all the individual elements that are then under consideration. So when we take a complement, A consists of B, C, and D, a complement says take the universal set and remove the elements that are contained within A. In other words, remove B, C, and D, and then everything that's left over within the universal set represents the complement. So that's going to leave us with A, E, F, and G. That's going to be a complement. Now B complement, same kind of idea, but now we're removing the elements that are specific to B. And we have to think of this as a brand new problem. We're not building on a complement. This is just B by itself. Look at U as the universal set, the context for the problem. Remove the elements for B and you get B complement. So B contains A, C, and F. And we want to visualize removing those from the universal set. So we're dropping off A, we're dropping off C, and we're dropping off F. So if you were to imagine covering those up, that's going to leave us with B, it's going to leave us with D and E, and it's also going to leave us with G. So that is going to be our complement. So again, think of the complement like subtraction. We're subtracting out one subset from the inside of the universal set. Everything that's left over after we remove those elements is what we're defining as the complement. Now the next operation is going to take two sets. So the complement lets us deal with one set at a time within the context of the universal set. The intersection is going to require us to have two sets in order to discuss what this intersection means. So the symbol, the notation for the intersection is going to be this notation. So the intersection of A and B is going to be A intersect B. This is actually an upside down U. It's not an N, it's a big upside down U. But in terms of remembering the notation, it kind of looks like a little lowercase n, right? So think N for intersection. It sounds like intersection. So whenever you see the symbol that looks like a lowercase n, it's again not a lowercase n. I don't want to see you write an n there, but it looks like it. So think of N for intersection. Now, what is an intersection? Think about an intersection between two streets. It's where the streets cross over, okay? So the intersection of two sets is going to be where those two sets cross over. So if we're defining it as its own set, its own new set, the intersection is all the elements that A and B have in common. It's going to be everything that's in A and in B at the same time. Now there's not really an algebraic way to describe this one, but if you think of what the word intersection means, you should be able to visualize what an intersection is. It's the things that are common to both sets. So in set builder notation, this is all X such that X is an element of A and X is an element of B. In other words, it meets both of these criteria at the same time. Not just one, not just the other, but both at the same time. This is one of the easiest things to identify in the Venn diagram because it's typically what stands out, particularly if we're looking at our standard two-circle diagram like this. The intersection is always easy to spot because it's that region right there in the middle where our circles are overlapping. So that is what we define as the intersection of our two sets. So it's easy to find it from a Venn diagram. Let's look at it from the standpoint of actual sets in roster method. So we have the set 7, 8, 9, 10, 11, and we're taking its intersection with the set 6, 8, 10, 12. So this symbol, again, it looks like a lowercase n for intersection. It's asking us, what do these two sets have in common, if anything? Well, how do you determine this? What if they're really long sets? Think of this kind of like a matching thing, kind of like we did with subsets. We're taking the elements in one set and we're trying to match them to the elements in the other set. Anything that we find that matches is considered to be part of the intersection. So if we start with the first set, let's start with 7. Can we match 7 to anything in the other set? No, so that means 7 is not in the intersection. Now what about 8? Well, 8 can be matched, so 8 is in the intersection. 9 cannot be matched, not in the intersection. 10 can be matched, so it is in there. 11 cannot be matched, so it's not in there. Now, do you have to repeat with the next set? The answer is no. If you didn't already match it, if it's over here and you didn't already match it, well, you're not going to be able to match it backwards. So you only have to do that with one set. Take each element, see if you can match it to something in the other set. If it does match, it's in the intersection. If it doesn't, then it's not. So in this case, the elements in the intersection, the ones that overlap, are going to be 8 and 10. Now what about the next pair? The first set is 1, 3, 5, 7, and 9. And then we're intersecting that with 2, 4, 6, and 8. Same idea. We want to start with the first set and see if we can match its elements to the things in the second set. So 1 does not match. 3 does not match. 5, nope. 7, 9. None of these elements actually match up with something in the second set. So if we define the intersection as the set of things that these two individual sets have in common, well, they don't actually have anything in common. But we can't just say no solution. The answer is not necessarily no solution. The answer is the set of things they have in common. Well, the set of things they have in common is actually the empty set. This is one of the reasons we define the empty set, so we can describe this particular situation. These sets don't have anything in common, so if we were to define the set of things they have in common, it's going to be the empty set. It's the set that doesn't have anything in it. And our term for this, we used the term a little bit further back when we looked at the diagrams. The term for this is disjoint. These two sets are disjoint because they have nothing in common. If they had something in common, then we can define it. If they don't, if their intersection is the empty set, we'll say that they are disjoint sets. Now, what if we have two sets written in set builder notation? Same idea. Now, as before, we've used this a couple times. You may want to take a moment and actually write out the contents in roster method so that you can actually see them. If you don't need to, you don't need to. But if you find you're struggling to identify what does and does not match, it's not necessarily a bad idea to take a moment and write out the individual items in the set. So our first set is all X such that X is a letter of the word create. So any letter in here would be something that's in this particular set. And then the second set is all Y such that Y is a letter in the word replace. So we want to know what's the intersection of these two sets. Where do they overlap? What do they have in common? Well, since we have the words, we essentially have the contents written out anyway. So we can do the same kind of matching activity just using what we already have. So let's start with the first step. We have a C. Can we match the C? Well, C matches, so that's going to be part of the intersection. Next we go to the R. R matches up to something, so that's going to be in the intersection. We have an E. E matches up, so that's in the intersection. A also matches up. T does not match up, so T is not in the intersection. And then we have another E. Technically, we have two E's in both of these words, but remember, it's not really good practice to write duplicates when we're talking about a set, because duplicates don't count towards our cardinal number. We don't really want to write duplicates if we can avoid it. So because we already have E considered part of the intersection, we don't want to necessarily duplicate it with that second E, even though that second E can be found in one word and the other. And again, we don't need to look at this next word, because if we didn't already match it, we're not going to be able to match it backwards. So our intersection is going to be the letters C, R, E, and A. So we've looked at the complement, we've looked at the intersection, we have one more set operation. We call this operation the union operation. So just like intersection has a meaning, like in context, in the real world context, think of what the word union means. Union means bringing things together. Marital union means joining two people together in marriage. Union is uniting, it's bringing together. So when we're taking the union of two sets, here's our notation for that. A union B, it's a big U, so think U for union, putting them together. A union B is all of the elements that are in A, in B, or in both. So in other words, picture joining the two sets together, putting all the contents of A and all the contents of B into one big set together. Now we use this word or in order to indicate that we can have it in one, we can have it in the other, or both. So in set builder notation, it's all X such that X is an element in A or X is an element in B. Or again means something very specific. It means it can meet one of these criteria, it can meet the other, it can meet both. That's not required, but we're allowing for the possibility that it does meet both. So again, think of just putting the two sets together and forming one big set with both of their contents. You can think of kind of like adding the two sets. If you were to identify this with something algebraic, it looks like we're adding the two sets together and just combining them into a bigger set. So in a Venn diagram, the union is going to be everything that lies in one or both of the circles. So to give you a visual of that, if we were to look at this particular one and take the union of the set A and the set B, well, everything that's in A is included. Everything that's in B is included as well. So if you imagine taking the circles together as one unit and taking all the elements that are somewhere in the circles as one big unit, then that's what we're thinking of as the union. So anything that's within the circles and then excluding anything that's outside of them, that's going to constitute the union in terms of visualizing it. Now, what if we have actual sets written out? Let's actually look at the same ones we looked at before. We took the intersection of these sets. Now let's take the union of these sets. So 7, 8, 9, 10, 11, and then 6, 8, 10, 12. I want to unite these sets together. In other words, combine them together into one bigger set that has all the contents that's in one or in both of them. So again, it's not necessary that you list things in order, but if we're talking about something like counting numbers, there is a standard order. So if you can list things in order, that's probably a good idea. Again, that's going to help you know whether or not you've missed something. If you leave something off, it's going to be much easier to spot if your numbers are in order. So the smallest number in the union would be 6. Notice 6 is not common between them. It does not matter. What we're doing is uniting these two sets together, combining them together, one bigger set with all the contents of either one of them individually. So we have 6 in the union. We'll add in the 7. Now notice the 8. 8 is an overlapping element. 8 was part of the intersection. When we write the union, we're not going to write 2 8s, even though each of these individual sets had an 8. If you were to think about what these two sets would look like in a Venn diagram, the 8 would be in the overlapping region. Well, it would only be written one time. It's part of circle A and it's part of circle B, but you would only see it that one time in the middle. So when you write it in the actual set notation, you're only going to write it the one time, even though it's actually contained in both sets. So 8, and then we have 9, we have 10, again common to both, only write it one time though, and then we have 11 and we have 12. So joining these two sets together forms this particular set, which has the contents of both of them. Now the next one, these two sets were disjoint. Remember, they had nothing in common. What happens if we take their union though? Well, the union just means we're joining together two sets that didn't have anything to start with in common. But when we join them together, we now have a larger set that has all the contents of either of them. So these numbers are actually going to alternate. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9 in order. Okay, and then the last pair, the ones we had in set builder notation, all X such that X is a letter in the word create, united with all Y such that Y is a letter in the word replace. So start with the first one here. You can put these in alphabetical order if you want. You can leave them in another order if you want, whatever seems easiest to you. Once you do it, you could then rearrange them and put them in alphabetical order if you want. So anything that's in the first set will be in the union. So C, R, E, A, T, those are all unique. That E is then a repeat. We don't want to write it. But C, R, E, and A, and T, those are all going to be in the union because those came from the first set. What we then want to know is what's added from the second set. What did we not have in the set in the union to begin with that is now added by uniting it with the second set? Well, we already have the R, we already have an E. P is new, so we're going to add P to the union. L is also new, so we're going to add that. And then A, C, and E, we already had those, so we don't need to write them again. So this is going to be the set we generate from the union. And this is not in any particular order. The order is just based on the order we saw the letters in. So if you wanted, you could rearrange that alphabetically. So what would that be? A, C, E, L, P, R, T? That would be perfectly fine as well. Either one is perfectly acceptable. So what happens when we have more than one operation? Just like in an algebraic situation, it's not always just adding or just subtracting. In a lot of situations, we have more than one operation involved in a particular expression. The same kind of thing can happen with set operations. And just like there's a standard order of operations in algebra, there's also an order of operations when we're talking about sets, when we're talking about the complement, the intersection, and the union. The notation, more importantly, is going to specify the order. So it's not going to be, we always do this one before another. It's going to be notation based. So what we're going to look for more than anything is going to be parentheses. Are they there? Are they not? If they're there, we always start with whatever operation or operations are inside of parentheses. So anything inside of parentheses, we always do first, and then we work our way outward. Otherwise, if we don't have any parentheses, we're always going to start with whatever can be done to an individual set one at a time, and that's going to be the complement. So if we're not looking at something where we have parentheses and then applying a complement, anytime we see the complement, it's applied to a single set. So that individual operation that applies to that individual set has to be done before we can link sets together, before we can take an intersection or take a union. Now, once we take care of that, once we take care of individual complements, things like that, then we'll just work left to right. So if an intersection comes first, we do that first. If a union comes first, we do that first. It's good practice to put parentheses just so it's clear what we're actually intending. But if they're not there, we just start with the complements and then we work left to right. So suppose we wanted to do A union B complement. Well, this particular expression has parentheses, so we have to start inside parentheses. So the first thing we'll do is take the union. Now, when we take the union, that's going to generate a new set. It's going to generate more than likely a larger set that contains all the contents of A and B. So So we're then going to substitute that in place of the individual A and the individual B. Now, once we've evaluated what's in parentheses, we then still have to apply the complement. But we're not applying the complement to A and B, we're applying it to the union. We're applying it to the set that resulted when we combined A and B together. Now, one thing I want you to be very, very careful about, this is a common mistake, a lot of people do it, it's not allowed. A lot of people look at this and think, well, this should distribute, right? In other words, if you're taking A union B and then applying the complement, you should be able to take A complement and take B complement and then take the union. That is not correct. You cannot do that. That would mean you can start outside and work your way in, which is not the case. You always start inside parentheses and work your way out. There is no distributive property when we talk about set operations. You start inside, you work your way out, and then you just work left to right. So you have to do the union first, and then you're going to take a complement of whatever set resulted. Now, what about something like this? We have A complement intersected with B complement. Here, there's no parentheses. Whenever there's no parentheses, we're always going to start with whatever operations are applied to individual sets one at a time. So in this case, that's going to be the complement. Notice we're taking the complement of A, and then we're also taking the complement of B. Those two complements are applied to individual sets, single sets, one at a time. So the first thing we want to do is take A complement and then take B complement. We can do that in 2 steps, or if you want, you could actually do those at the same time. So if you're looking at an actual problem with actual sets, you can do both of those complements at the same time. But you have to do those before you do any operation that combines anything together. So A complement, in other words, take the universal set, delete A. B complement, take the universal set, delete B. And then you want to take the intersection of the 2 sets that result from taking those 2 individual complements. So let's look at a few examples. What happens when we have a set given in set notation? What happens when we're looking at something like this from the standpoint of a Venn diagram? This is going to be a situation where showing your work is important, particularly when there are several layers. When you're combining different operations together, it's the same thing as if you have a multi-step algebraic problem. You don't want to try to do it all at one time, because if you make a mistake, it's going to be next to impossible to figure out where the mistake was made. So by doing one operation at a time and writing down the result from that, that's going to help you determine what happened if you end up making a mistake. So let's look at the 2 operations that we had described on the previous page with these specific sets. So our universal set is all the natural numbers from 1 to 10. A is going to be 1, 3, 7, and 9. And then B is going to be 3, 7, 8, and 9. So the first set we want to find is going to be A union B complement. Now we know we have to start inside parentheses, so the first thing we're going to have to do is take that union of A and B. Now here's where I'll kind of leave it up to you. You can, if you want, write down your A and then write down your B and then take the union having them listed side by side. That's an option. Or if you think you can just look at them above, since they are listed out, and just write down the union from looking at them here, that's perfectly fine as well. It's ultimately personal preference. Once we start building in more operations, I'll encourage you to write down a little bit more, but here we can probably just look at these and determine the union. So remember, the union means we're taking A, putting it together with B, combining them into one larger set with the contents of each of them. So A and B join together, we're going to have 1, a 3, a 7, an 8, and a 9. So there is some overlap between these 2 sets. Remember, we only write the overlapping elements one time, so we get 1, 3, 7, 8, and 9. That's going to be the result of the union. Where we're taking the result of the union and we're taking its complement. In other words, we're taking that new set that we generated and we're pulling it out of the universal set. We're taking all of those elements, removing them from the universal set, and determining what's left if we do that. So if my union is going to be 1, 3, 7, 8, and 9, then when I take the complement, I'm removing these specific elements from the universal set. So if I remove these elements, I have to determine what's left over. Well, 1 comes out, 2 is left, 3 comes out, 4, 5, and 6 are left, 7, 8, and 9, all 3 of those come out, and then we're left with 10. So our final set is going to be 2, 4, 5, 6, and 10. That is going to be the result of taking the union and then taking the complement. Now, as I mentioned on the previous page, you cannot distribute that complement operation. You can't take A complement and then take B complement and then just say combine them together. You might verify that here, that if you try to do that, you get a different answer, because you will get a different answer. It's not going to be the same thing. Okay, let's look at the other one. So A complement intersected with B complement. Here we have to do the individual operations, the individual complements, before we can do anything that requires 2 sets to be combined together. So A complement first, and then B complement. So A complement is going to take all the elements in A, remove them from the universal set, and then we determine what's left. So if you remove a 1, 3, 7, and 9, we're left with 2, 4, 5, 6, 8, and 10. 2, 4, 5, 6, 8, 10. Now B complement, same thing, but we're removing the elements from B. So remove 3, 7, 8, and 9, which leaves us with 1, 2, 4, 5, 6, remove 7, 8, 9, so we have 10. So 1, 2, 4, 5, 6, and then 10. So those are the results from the individual operations applied to the individual sets. And now we're taking the intersection of those 2 results. In other words, we're looking at those 2 new sets and we want to determine what, if anything, do those sets have in common. Well, let's start with the first one. Remember, this is essentially a matching kind of thing. So we want to look at each element, see if we can match it to something in the intersected set. So 2 we can match, that's in the intersection. 4 matches, 5 matches, 6 matches, 8 does not match, and then 10 matches as well. So 2, 4, 5, 6, and 10. That's going to be the result. Now let's do the same kind of thing, but let's do it with a Venn diagram. Keep in mind what these different operations mean. So complement means remove the set from the diagram. Intersection means we're determining where the subsets, in this case the circles, overlap. And union means take the circles, put them together, think of them as one big unit. So we'll start small and then we'll build on. So A intersected with B. What's that going to be based on this particular diagram? What are the contents in A intersected with B? Well, the intersection, again, that's the easiest region to identify. It's the region where the circles overlap. It's going to be this region. So A intersected with B is just going to be 5. Remember the Roman numerals, those are just labels. So the element in the intersection is going to be 5. Now what if we wanted to take A intersect B complement? Well, that's going to take the previous result and then we just take the complement of that. Visually, remember the complement means subtraction. It means you're pulling that set out. So we're taking A intersected with B and we're removing it from the diagram. In other words, think about the region that's represented by that intersection and remove it from the diagram. So I'm removing this section from the diagram, and anything that's left over anywhere within that rectangle represents the complement. So everything that's in A exclusively, everything that's in B exclusively, and then anything that's outside of the subsets. So 1, 2, 3, 7, 11, 13, 17, and 19. So everything except for that number 5. Now what about A union B? Now we're taking our 2 sets and we're joining them together. So anything that's in A, anything that's in B, join it all together, make one big set with all of it. So everything from A, that's going to be 2, 3, and then 5. 5 overlaps. And then anything additional from B. So that's going to be 7, 11, and 13. So that's going to be our union. So again, imagine just taking the circles as one unit. In other words, the only things that are not included are going to be the things that are outside of the circles entirely. Anything that's in the universal set, not further grouped into the circles, is not part of the union. Well, what if we take A union B and then take its complement? Well, we're taking the result of the union, which was everything within A and B as one big unit, and then we are removing it. We're subtracting that out. So that would take this joined region and it would remove it entirely from the diagram. So anything that's left over once we remove those, that's going to be part of the complement. So in this case, 17 and 19. So A union B complement, if we want to describe what that represents everything that's in the universal set outside of the circles. So anything that's in the universal set that wasn't grouped into A or B, this is the way we describe that particular set of elements. Now let's do some where we have to build on one at a time. So A complement union B. Do this one at a time. We want to take A complement and then we're going to unite it with B. So A complement, let's actually write everything out in set notation, go step by step. We want to do A complement first because that applies to an individual set. So A complement says take A, remove it from the diagram and see what's left. So we're taking out the set A and determining what's left. So in this case, we have everything that was exclusive to B, and then we have the values that were neither in A nor B. So 7, 11, 13, 17, and 19. That's going to be the values within the complement. Now we're uniting that with B. So the set B is defined as anything that's in the circle for B, which includes 5 in the overlap. So 5, 7, 11, and 13. Those are going to be the elements within B. So we're now taking the union of those two sets. We're bringing them together, uniting them together, creating one bigger set with all the contents of the individual ones. So 5, 7, 11, 13, 17, and 19. That's going to be the set representative of this particular operation, the sequence of operations. So what's not included here? Well, the only things not included here are going to be the 2 and the 3 that were in the set A, that were exclusive to A. So we can think of this particular thing, this particular construct, as representing everything that's in U except what was exclusive to A. Anything anywhere in the diagram is included as long as it wasn't exclusive to A. What about A intersected with B prime, B complement? Now again, we need to go step by step, start with the complement. So B complement says, take the set B, remove it from the diagram. So remove the set B from the diagram, see what's left. We've got our 2, our 3, and then we have a 17, we have a 19. So that is going to be B complement, 2, 3, 17, 19. Now we're intersecting that with A, so anything that's anywhere in A, which includes 2, 3, and 5. Now we're taking the intersection, which means we're overlapping these two. What do these two sets have in common? Well, the only elements they have in common are going to be 2 and 3. So A intersect B prime is going to be 2 and 3. What does this represent? It represents everything that's exclusive to A. In other words, everything that we excluded in the previous one now is included in this one, and vice versa. So this one excludes all the values in the previous one. This one excludes the values 2 and 3. So we could think of these two sets being complementary in a sense. One is the opposite of the other. But keep in mind, what would happen if you took these two sets and joined them together and took their union? You'd have 2, 3, 5, 7, 11, 13, 17, and 19. In other words, you'd have the entire universal set. So a big takeaway there, something to think about. If you take a set and combine it, unite it with its complement, automatically you form the entire universal set just based on what the complement operation means. It means take a set, pull it out. Well, if you take a set and take its complement and join them together, you essentially are generating the entire diagram. So this gives you a few examples to look at just based on the different operations we can do, the orders we can do them in. Just keep in mind, parentheses always come first. Then you do operations working your way inside, outward. If you don't have any parentheses, individual complements to individual sets come first. And then you just work left to right with your unions, with your intersections. Okay, let's talk about one more thing, and then we will be finished. Cardinalities, counting. One thing we're going to be interested in is not only representing a Venn diagram with specific individual elements, but more importantly, counting how many elements are in specific sets and specific regions within the diagram. Now, counting for an intersection is usually pretty straightforward. You're just looking for whatever your two sets have in common and just counting how many elements they have in common. So the cardinal number for an intersection is going to be n of A intersect B. So the n of notation, that's our cardinal number notation. If we want the cardinal number for the intersection, we're just going to write the intersection, and that tells us we're counting for that particular region. And again, that just means look at the sets, identify what they have in common, just count those. Now, if we're counting a union, it's a little bit different. It's a little bit more complicated. If you think of the union as essentially representing set addition, you might immediately think, well, just take the number of elements in each set and add them up. Intuitively, that sounds right. But that's not the whole story. That actually overcounts. If you were to take just the elements in each set, so elements in A, elements in B, add them up, you're actually going to get a count that's typically too high. The reason it's going to be too high is because doing that actually double counts the overlapping region. Think about it. If you have A and you have B, think of everything that's in A, count everything that's in A, count everything that's in B, add up A, add up B. Well, what happened? If you think of that overlapping region, that was counted as part of A, and it was also counted as part of B. Even though those elements are only in the diagram one time, if they're counted as part of A and then also counted as part of B, then they've been counted more than they're really there. They've been double counted, which is going to give you a total that's just a little bit too high. So you are going to add up the cardinal numbers for the individual sets, but you have to do a minor adjustment. You're going to take the cardinal number of one set, add the cardinal number of the other, but then you want to subtract the cardinal number for the intersection. So the number of elements in A union B is going to be the number of elements in A, the number of elements in B, minus the number of elements in the intersection. So how does this formula work? Why does it work out the way we want it to? Well, if you think of the elements in A intersected with B, they're both in A and in B at the same time. So they were counted here one time, they were counted here a second time. We don't want to completely throw them away, but we want to make sure we only count them one time. So if we counted them here once and then counted them a second time, by subtracting out that additional count, we reduce that double count and we override what we did when we double counted. So that's going to give us the correct total. Okay, so let's revisit our donating blood example. We now have the results. So some of the results indicated that 490 students were willing to donate blood, 340 students were willing to help serve breakfast, and 120 students were willing to do both. How many students were willing to donate blood or serve breakfast? Now, one distinction I want you to start making, you're going to have to be careful about wording. Notice it says 490 students were willing to donate blood. What it does not say is 490 students were willing to only donate blood. If you don't see the word just or the word only, something like that, that's telling you this set exclusively, then you have to assume something like 490 is a total. So this means that 490 students in total were willing to donate blood. This includes students who only wanted to donate blood, as well as the students who wanted to do both. So we're going to consider these to be totals unless you see something like the word only donate blood. Then and only then can you think of that number as exclusively representing that particular set. Same thing with the 340. 340 students were willing to serve breakfast. Well, not only serve breakfast, 340 students in total were willing to serve breakfast. So again, that includes people who only wanted to do one thing, as well as people who are willing to do both. Now, we do have to be told who's willing to do both things. So notice in this case, 120 students were willing to do both. So we do know how many are in the overlap, how many fall into category A and category B. And knowing this, now we have enough information to determine essentially the count for the union. So this word or, this is what tells us we're looking at the union. We want to know who's donating blood, who's serving breakfast. Think of it as determining all the volunteers. So maybe the idea is you want to make t-shirts, you want to make name tags, something like that. You need to know how many t-shirts or name tags you're going to need. Well, if you just add up your 490 and 340, you're going to have more than you actually need, because that double counts the people who are willing to do both things. So the count for our union, the cardinal number for our union, people who are willing to donate or help with breakfast, that's going to be everyone who wanted to donate, 490 people in total. Everyone who wanted to help with breakfast, 340 in total. This double counts people who did both. So we're going to subtract that overlapping region so that it's only counted the one time, and we override it being counted the second time. So 490 plus 340 minus 120. And of course, you can simplify that in your calculator if you want. So 490 plus 340 minus 120, that's going to give us 710. So that means we had a total of 710 volunteers. Some of them only wanted to donate blood, some only wanted to help with breakfast. 120 of them exactly said they were willing to help with both things. Okay, let's look at one more example. Among the US presidents in the White House, 26 had dogs, 11 had cats, and 9 had both dogs and cats. How many presidents had dogs or cats? In other words, if they have a dog, they count. If they have a cat, they count. If they have both, they count. Again, just like before, we don't see the word only anywhere. We don't see only dogs. 26 had only dogs, or 11 had only cats. So we have to assume that that 26 and that 11 are totals. 26 people in total had dogs, 11 in total had cats. So if we want to know how many had one or the other, thinking about what or means in this context, one or the other or both, we're going to add up how many had each type, the totals. So the count for the union is going to be 26 plus 11, which overcounts the overlap. So we're going to subtract the count for the overlap. So let's do this one. So 26 plus 11 minus 9. Yep, that looks right. That's going to give us 28. So 28 presidents in total had one pet or the other, had a dog or a cat. So we've introduced these set operations. We know what they look like in the context of a Venn diagram. We know a little bit about interpreting a Venn diagram, looking at what we see, identifying the different regions, what they mean. In the next section, we're going to add on an additional set. So you can form Venn diagrams with as many sets as you want. We're going to cap it at 3, but we're going to talk about what the diagrams look like in that context and how we do set operations when we have 3 sets.